Okay, the shaft shown below is subjected to a force of 1.75 kilonewtons and axial force P equals 9 kilonewtons and a torsional load of or torque of 72 Newton meters. The material used is aluminum with a yield strength of 276 megapascals. Using the table shown below and design factor ND equals 4, select a stock size for the shaft and compute the factor of safety. Assume one misses stress as a failure criterion. So one misses. Okay, this is a typical design problem you might come up if you are trying to do this for uh, to design something, right? This is a rather simple geometry. It's just a shaft with, it's actually a solid shaft, not even a hollow shaft. Uh, the element which is going to have higher stress is typically on the outer surface here because the geometry same. There's stress concentration where A joins the wall, but let's ignore that. The stress concentration will only make the stresses go higher, and you can account for that by doing the calculations which we did some time back. Or you could just put a factor of safety and say that that accounts for the stress concentration. So up to you. But when you know things, you normally want to calculate them. Okay, so let's see. So we have uh, F, we have P, we have a torque, and we know that anywhere on the surface is going to be the highly stressed part of the shaft. Okay, so remember you are given this, but you're not given the diameter. Okay, uh, in fact, the diameter is here. Okay, what is this? What does this mean? It's basically, oh, sorry, my bad. This is a hollow shaft. I did not see this. This is actually a hollow shaft. It has, and this is something which I should probably give you before. So this is, what this indicates is the diameter, which is shown here, and also indicates the thickness. So the thickness is right here, right? Thickness. Okay. So it does some work for you. It has basically given you a table of the cross-sectional area. Again, my bad. I should have given you the units. Oh, it's given here. My bad. It's all given here. Yes, it's given here. So they have done this work. You could also do this calculation yourself. You could compute the area, uh, second moment of inertia, polar moment of inertia. I don't think we need radius of gyration here. Section modulus is needed if you are looking at bending. Anyway, it's all available to you. Okay, so what we'll try to do here is the same thing. We're going to try to compute the one misses stress. That's the first step. And hopefully that one misses stress is going to be a function of all these parameters, A, K, A, I, J, and then that will give us, for each of those values, we'll get a design, a one misses stress. And based on that, we would perhaps figure out which stock size will give us the appropriate factor of safety. So what's given here is ND equals 4, and then we also given that the yield strength is 276. And so we know that ND is, it's the maximum stress, which will be the yield strength divided by the one misses stress. So what will happen here is we know this, we know this, this we can now compute because it's straightforward based on those two values. And this design will give us a certain one misses stress. And it's just a matter of figuring out what one misses stress will give us the appropriate value, which doesn't lead to greater than that value. Okay, so let's get started. It's essentially a similar process like before. So the three steps are: one, compute uh, stresses. Okay, in this case, if you look at the element A, it looks like it's in the XZ plane, Z being here, X here. So you will end up with an element which looks like this. So I'm going to draw this exactly like it is here. X is this way. So sigma X, sigma Z, then tau ZX, tau ZX. Okay, so the first step is to compute sigma X, sigma Z, tau ZX. Okay. Next step is we can compute sigma prime. Here we don't really have to worry too much about principal stresses because you know a formula for sigma prime in terms of principal stresses. So sigma x square plus sigma z square minus sigma z sigma x plus 3 times tau zx square. We wrote that formula earlier. And then the last step is to use this equation sy by sigma prime to and this table to choose stock size solve. So we've broken it down. Let's get to solving this. Let's try to identify the stresses, sigma x, sigma z, and tau zx. Shaft. So there is a normal force. There is a load this way, and then there is torque. And we are looking at an element here. This is the x-axis. This is the z-axis. And the y-axis are not very important, but they will be up. Sigma x, sigma z, tau zx. Okay, well said. Okay, so first of all, let's try to compute sigma x. Okay, so what leads to sigma x? Okay, so we just have to see ask the question: does capital F lead to sigma x? What do you think? It will, right? It will lead to sigma x through moment, bending. So when F is applied, this thing is going to sag, or it, in other words, will lead to a moment. And this moment is along the z-axis because this is the z-axis. And that will clearly cause the top plane to have tension. So sigma x will be positive. So sigma x on top would be m. Oh my God. Okay, thank God. It didn't go away. This is y. Well, y here in this case is d divided by 2, right? So m times d divided by 2 divided by I. Oh my God. Yeah. So this is the formula my divided by I. And then we should remember it's positive because A is the top one, which will have tension. Okay, we can also figure out what M is. Okay, so M is going to be, is simply force F times the distance. I should have put the distance. This is 120 mm or 0.12 meters. So M is known. Okay, so that's due to F. Does the torque lead to sigma X? No, right? Only shear. What about P? Does P lead to sigma X, a stress in the X direction? It will, right? It's a uniaxial, uh, it will be through a uniaxial tension, it will cause a stress. And it'll actually be a positive stress the way P is shown. So it's going to be P divided by A. So we've identified sigma X. Now an aside, what about a point here? Let's say this is B. So sensitive. So the thing is, I got a new one, but then I realized that I only have two two USB-Cs and need one for the power and the other one for my this. And so I just need to buy another one. Yeah, I, I need to buy one. That was very good till one day it stopped being good. Something happens to it. Let's see if it comes back to here. There it is. Okay, so aside, this is actually uh, one of the reasons why I chose the point. Will become clear probably. So if you have a point B, I should draw the different color. Let's say this one, it's B. What will be the sigma X at B? So there would be a moment, right? But this point here is under compression. So this will be minus md divided by 2 by I, and then the stress P will cause a uniaxial stress. So that is no doubt positive. So this is the difference, I guess. So you see this is a negative sign, this is a positive sign. That stress is lower than the stress I compute at A. The stress at B is lower because of the negative sign, and it's higher at A. So just by playing with the points, you can get different stress. What about a point here? What about this point? Let's take this point. What is the stress here? Due to, let's say, due to P, it's P divided by A. What about the stress due to M or F, sorry? It'll be zero, right? Because it's neutral axis. Okay, so that's no wonder why I chose A, though that's something you need to figure out before you do this. It's not going to be the same stress due to F. It's going to change, but the stress due to P is constant. 3 o'clock, yeah, then you'll have to just sub in the right Y, right? You'll have to see if it's above, which will be positive stress, or below, negative stress, and then you just substitute the right Y. So at 3 o'clock, you need to find the Y by using, by computing the height at that point. No, it won't be. Y is the distance from, so you're saying, if, so you're saying this point. No, 3 o'clock, 3 o'clock is zero. At 2 o'clock, the height is whatever that is. Yeah, cosine or sine, depending on how you choose the angle. Okay, so we got one of the three stresses. let's compute sigma z. Okay, so is there a sigma z? What about F? Does F produce a sigma z? We know that it doesn't. P doesn't produce, it's a uniaxial stress. Uh, what about T? It doesn't produce a normal stress, so that should be 0. Okay, and finally, tau Zx. Again, so we do the same thing. Capital F won't produce a shear stress. P will then produce a shear stress. The only shear stress which occurs is due to the torque T. We know how that to compute that. That's basically T times use I think rho divided by J. So rho in this case is the diameter divided by 2. So let me do it this way. T times d divided by 2, and this comes from the formula T times rho divided by J. So that's it. So those are the values. Okay. F is given, so let me just sub in that value. F is 1.75 kilonewtons. So this is 1.75 10 raised to 3 times 0.12. And then this is also given torque. It's given as 72 Newton meters. So that's known. What is unknown here is, I'm going to show that in pink. This P is known. I should put that value. So P is given. It is 9 kilonewtons. So 9 times 10 raised to 3. So the unknowns here are I, D, A, and here D is unknown and J is unknown. Okay, so that's the step 1, which is computing the stresses of sigma x, sigma z, and tau zx. Okay, next step is to compute, we're done with this. Next step is to compute the von Mises stress, sigma prime. Okay, so the von Mises stress is sigma x square plus sigma z square minus sigma z sigma x plus 3 times tau x z square. So this would be sigma x is P divided by A plus, I think I put 0.12 F times T divided by 2 divided by polar moment, second moment of inertia. So this whole thing squared. So sigma z is 0. This will also be 0 because sigma z is 0. And then 3 tau cx square would be the torque times T divided by 2 divided by J square. Okay, so again in this, A is unknown, I is unknown, D is unknown, D is unknown, J is unknown. These are the unknowns. Okay, because those are design parameters. We need to choose that. Okay, so that's that. We can't do much with that. Let's do the third step. And third step was to compute sigma prime. It's ND SY divided by sigma prime. So that is ND is SY divided by sigma prime. So ND is 4. The principal, the yield strength is 276 MPa. Just to 6. And then sigma prime is unknown. So we have sigma prime is So I get 69. I actually wrote it in 69 megapascals. So you don't really need to do 10 raised to 6. Okay, now let me name this. Let's call this equation 1 and equation 2. Okay, so very close to getting the design completed. Okay, so on one side, we know what the von Mises stress is, but we don't know what the parameters are. So clearly, we can sub in the value for P, F, and T, but we still have to get D, I, and A. So what you need to do is this. Go to this table, choose a stock size. So let's say we chose this one. You're given A. So go back to this formula, put in the value of A. Look at I, put in the value of I. Similarly for J, put in the value of J. And then you also given the diameter. This is the diameter, right? D times T. So for a given stock size, you would know capital A, I, small d, and J. And then you'll get a sigma prime. And you need to do it for every single value till uh, you find the biggest possible value, but less than 69. Okay, so this is probably most easily done if you perhaps use Excel or some kind of a programming environment. So what I did was I think I used MATLAB to make a table. This is what I did. I took D, I took A, I took I and J, the four things. And then I computed sigma prime using formula one. What's formula one? It's the one I wrote down here. It's this one, right? If you know A, I, D, and J, you can compute sigma prime. So that's the step one. I got this. And these are all MPAs, right? This is actually pascals. So then you have 10 raised to 6, but you can eliminate that. Then it'll be MPA. Now, you also know that the maximum von Mises stress is 69. I cannot exceed 69. Otherwise, we'll exceed the factor of safety. So what we need to do is we need to use 69 and scan through the table and see. So this stress is 174.75 MPa. That's way too high. This is way too high, 179. Oh, I think there's probably some error here. I think it's 179. It's clearly not this small. Yeah, but then 174 doesn't look like. Yeah, so there's some problem here. I'll fix that, but it's clearly high, so not even close to 69. Anyway, keep going. 140 to 1, this will not do either. So this is where you can have a decision, right? This is the larger stress, which is still less than 69 times 10 raised to 6 Pascal. This is from equation 2. Equation 2 was written down here. Okay, so clearly we see that we can use this particular stock size. Should be what will make the cut. Okay, so the first question was compute identify the stock size, and we saw that the stock size, which makes sense, is 42 cross F, which is T times T, is shown here. The second step is to compute what the factor of safety is. So the factor of safety is the maximum stress or yield strength in this case, divided the von Mises stress. The maximum stress is 276 MPa, and the von Mises stress now is not 69. That was based on design. The actual stress is going to be 60.4. Comes from there. And so this gives me 4.56. So the factor of safety 5.6. So started with a design factor of 4, but ended up with a factor of safety of 4.56, a higher factor of safety. And that's because the stock size I'm looking for to get exactly 4 is not available. I need to go for a bigger size. A bigger size would mean that the factor of safety would increase. The design is more beefier than it should be, but that's okay.